Hi, welcome to the video on performance of three-phase induction motor on load with its phasor diagram and the equivalent circuit, referring to it, just like a transformer. So, coming to the performance of this three-phase induction motor on load, the phasor diagram of loaded induction motor is similar to the loaded transformer. The only difference is the secondary of the induction motor is rotating and short circuited while transformer is stationary and connected to load. So the load on induction motor is mechanical while load on transformer is electrical. Still, by finding electrical equivalent of mechanical load on the motor, the phasor diagram of induction motor can be developed. Now, let us say this is the flux produced in the stator. So the flux produced in the stator is denoted as phi. So the EMF induced in the stator because of this flux is, in the stator per phase is E1. So E1 is induced voltage in rotor per phase. So because of the, induced voltage in the stator, it also, have because of the mutual induction, EMF is also induced in the rotor. So rotor induced EMF per phase is also denoted as E2R, that is under running condition, which is in the same phase as E1. So if V1 is the supply voltage, and we always know that the induced EMF opposes the cause producing it. So we need to have the stator EMF induced E1 is opposing the cause producing it. So it is minus E1 here. So E2R. Now coming to the rotor induced EMF in running condition. So we have E2R in phase and we have I2R2. I2R is lagging E2R by an angle phi 2R. So we know that the rotor current now, which is in the rotor side, because of this induced EMF, it develops a rotor current which has a phase angle difference of phi 2R with respect to E2R. And we know I2R and R2 of rotor is in phase with I2R. Okay, and the I2R X2 of rotor is exactly at 90 degree with respect to this I2R R2. So now completing this vector, that is I2R2, I2RR2 and I2RX2 gives the resultant, that is I2R into Z2R. So we always know that IM, that is the magnetizing current which magnetizes the core, is always in phase with the flux. So this is IM. So IC is the component which is core component which is perpendicular to this IM. The resultant of IM and IC is I naught. So this is the I naught value. And now we know that the stator current I1 is the resultant of this I naught and the I2 dash R2. So if you reverse this I2R, if you reverse this in terms of, it becomes I2R dash referring to primary. So dash refers to primary. This is the rotor side. So when you refer to primary, it becomes dash. So reverse this vector, that is I2R. The resultant of I2R and this I naught will gives the stator current, that is I1. Now coming to the stator, we have I1 R1 in phase with I1 and I1 X1, that is exactly 90 degree with respect to I1 R1. So if you draw this, the vector sum of I1 R1, I1 X1 is the resultant vector I1 Z1. So this I1 Z1, okay, the resultant of E1 and I1 R1 and I1 X1 will give you the voltage supplied to the stator, that is V1. So V1 can be written as okay. So the I2R current is running condition. So we know that I2R is E2R by Z2R. This is the current I2R. So I2R is equal to E2R divided by Z2R. Okay, this is the stator side and this is the rotor side. And we can just write just like referring to a transformer, it appears like this. This is the exciting circuit, that is the core exciting component. So that is how we draw the phasor diagram. So coming to the next point here, So we have already seen that induction motor can be treated as generalized transformer. So transformer works on the principle of electromagnetic induction. So induction motor also works on the same principle. The energy transfer from stator to rotor of the induction motor takes place entirely with the help of a flux which is linking this winding, the stator winding and the rotor winding. The stator acts as a primary while the rotor acts as a rotating secondary in induction motor. Okay, so if E1 is the induced EMF in the stator and E2 is the rotor induced EMF per phase at standstill, so under running condition it will be S into E2, which is referred as E2R, which defines under running condition. So if V1 is the supply voltage per phase to the stator, it produces the flux phi, which links this both the stator and the rotor. So due to self induction, E1 is produced here and the EMF also induced in the rotor, that is E2, due to mutual induction. So at standstill we take S is equal to 1. In running condition the slip has to be introduced in the rotor, so it becomes S into E2. So now E2R is the rotor induced EMF in the running condition, R2 is the rotor resistance per phase and X2R is the rotor resistance per phase in running condition. So R1 is the stator resistance and X1 is the stator reactance. So induction motor can be represented just like a transformer as shown here. So when induction motor is on no load, it draws a current from the supply to produce a flux in the air gap and to supply iron losses. So IC becomes here active component which supplied no load losses. IM is the magnetizing component which sets up magnetic flux in the core and air gap. These two currents gives us the element of an exciting branch. So where R0 and X0 is representing, this R0 represent no load losses, this represent the flux setup. So equivalent, the vector sum of IC plus IM gives the no load current I0. So the basic equivalent circuit, so can be, rotor equivalent circuit can be written in the, considering only the rotor side, it is E2R R2S X2 into I2R. So I2R is the rotor current running in running condition. So E2R is equal to, I2R is equal to E2R divided by Z2R, where Z2R is equal to R2 square plus SX2 whole square. So it is important to note that as load changes on the motor, the speed also changes. Thus the slip changes. As slip changes, the reactance X2 also changes. Hence, X2R is equal to X into X2 as shown. Now, if I have to represent this rotor impedance, okay, if I have to represent this I2R as a rotor impedance, it is said I2R is equal to S into E2 by square root of this, which is represent. Now, voltage E2 is fixed, but a variable resistance R2 by S as indicated in the above equations. Let us simplify this. So, dividing this by S throughout. So, this becomes E2R is equal to E2 R2 by S into X2. So, this is the circuit we get. R2 by S into X2. So further, this R2 by S can be simplified because some part should be taken as a fixed term and the other part can be taken as the load resistance. So we can define this R2, just, rearrange that. We can say that R2 by S is equal to, R2 by S is equal to R2 plus R2 by S minus R2. So somewhere we have here R2 by S, one second. Yeah, this one, simplification. So R2 by S can be simplified as R2 plus R2 into 1 by S minus 1. So if you take, R2 plus R2 by S minus R2. So if you take R2 as common in these two terms, so it becomes 1 by S minus 1, and further simplification R2 plus R2 into 1 minus S by S. So we'll denote this R2 into 1 minus S by S as RL dash and R2 as it is here. So this circuit changes like this now. So this is the circuit we get X2 R2 and R2 into 1 minus S by S is denoted as RL. So now to obtain equivalent circuit referred to this, stator. So I have to refer this rotor side to the stator. So look at this. So when I refer this to the stator, we denote this with in terms of dash. So X2 dash, R2 dash, R2 dash, into 1 minus S by S, and it is connected to the primary side. So this EMF becomes E2 dash, and the current in the rotor side becomes I dash I to R dash. So this is the equivalent circuit of referred to the stator. So approximate equivalent circuit. So moving this exciting circuit towards the supply side, this is the circuit we get. The now resistance R1 and R2 dash can be considered as R1E. X1 plus X2 dash can be considered as X1E. R2 dash into 1 minus S by S as RL dash also. So this is the equivalent approximate equivalent circuit of a three-phase induction motor, where I1 is equal to I0 plus I2 R dash, where I0 is equal to IC plus IM. So power equations from the equivalent circuit, if you look at it, the power input to the induction motor is three-phase power. So that is 3 into V1 I1 cos phi, where V1 is the stator voltage per phase, I1 is the current drawn by the stator, and phi is the power factor between this V1 and I1. So stator core loss will result with respect to Im square R0, and stator copper loss with respect to 3 I1 square R0, where R1 is a stator resistance per phase. So if P2 is the rotor input, we have seen the power flow diagram. When you refer the power flow diagram, which has already been discussed in the previous video, power input P2 is equal to 3 times of I2 R dash square into R2 dash divided by S, where PC is the rotor copper loss, that is 3 into I2 R dash square into R2 dash. Thus PC is equal to S into P2. So if you refer this PC and P2, if you relate, this will be PC is equal to S into P2. So PM is the gross mechanical power developed, that is P2 minus PC. So referring to power flow, you can derive these equations what I have explained here. So PM is equal to P2 minus PC. So when you subtract P2 minus PC, you get 3I dash 2R square into R2 dash into 1 minus S by S. So torque developed is also mechanical torque developed is PM by omega. So substitute this PM and omega as 2 pi n by 60, and further substitution and solving, we get torque as value as 9.55 into this divided by S in divided by NS. So key point, so all are in per phase value. So remember, we are deriving this power equations for per phase values. Thank you for watching this video.